One last piece on our intro to series section here, 11.2. So 11.2, our intro to series, we are looking at these infinite sums, these series, and trying to determine if they converge or diverge. And so there's one theorem and a test that come at the end of this section. The theorem is this. It says that terms in a converging series, if we have a converging series, a series is convergent, meaning that its partial sums have a finite limit, then the limit of the actual terms that we're adding up must be equal to 0. So hopefully this intuitively makes sense. I'm going to skip over this divergence test explanation for just a second. And let's take a look at this visual right here. Remember that when we are testing a series for convergence, trying to determine if a series converges, we are actually looking at what happens to the partial sums as n goes to infinity. So if we look at the partial sums and we actually graph the partial sums, notice on this graph, this is the graph of the partial sum. So the graph that we're looking at right here is the graph of the actual partial sums of some series that we're looking at. So we're graphing the sequence of partial sums here. That's what those dots, S1, S2, S3. So each time we're continuing to add another term for each of those partial sums. And if those partial sums has a limit, which this one does, then you have to think about the fact that each time you're adding something, you must be adding something that is approaching 0. Otherwise, it would never approach a finite sum. So hopefully intuitively that theorem actually makes sense to you. And that is where we get this first test for divergence. Actually, it's our only test for divergence. Our following tests that come after this particular test will be test for convergence. So this is called the divergence test, and I'm going to list out our test in this form for all of them, kind of in a nice little organized form for how do we test series for convergence, or in this case, divergence. And so the name of the test is the divergence test. We're looking at some series. Doesn't matter where the index starts. It says k equals n to infinity of a sub k. And in this particular case, we are not actually testing for convergence. We are testing for divergence. And the test says this: if the limit of those terms does not equal 0, then that must mean that the series converges. And that is all that this says. This doesn't tell us anything else. So in the comments box over here, this is actually an important comment. If the actual terms in the series go to 0, we know nothing else. And we'll look at some examples about that. It tells us nothing about the convergence or divergence. So if the terms go to 0, great. We don't know. We got to do something else. Okay? So if the actual terms do go to 0, then we have to actually do something else to determine the convergence or divergence. But if the terms do not go to 0, if we can show that the limit of the terms in the series, not the partial sums, but the terms in the series, do not equal 0, then we would know right away that the series itself must diverge by the divergence test. Okay, so that's the theory, and we're going to apply it to a couple of examples, and then we'll look at one where this piece that I mentioned right here in starred will become very clear, where just because the terms go to 0 doesn't actually mean anything to us, whether we have convergence or divergence. All right, so, and this is, again, I wanted to just really reiterate this point. If the limit of the terms equals 0, we know nothing about the actual series. So keep that in mind. We'll come back to that in a few different examples over time. So let's take a look at this. If we had this particular example, and I'm going to take it actually over here, so I have a little bit more space. So let's look at an example here. Let's suppose we had the series of n squared over n squared minus 3n plus 1 from n equals, what did I start at? 1. From n equals 1 to infinity. So when I come across a series that looks like this, the first thing I'm going to think about, actually any series, the first thing I'm going to think about is what is the actual limit of the terms. And I might do that just in my head. I might do that by writing it out. Certainly if the limit is not going to be equal to 0, then I'd want to write it out because that's how I'm going to prove divergence. So the limit of n squared over n squared minus 3n plus 1, what is that going to be? Well, at first glance, of course, that's just infinity over infinity. So we've got our options, right? We could go L'Hopital's rule. We could just work with the powers of a rational function, p of x over q of x, or we could even divide by the highest power in the denominator. So a little flashback to Math 30, highest power of the denominator. So little flashback to Math 30, go with whatever you want to go with. You've got lots of tools in your toolbox now to deal with this limit, but I'm going to just come in here and say, what if we just divided everything by n squared? I like to vary it up, use a variety of different techniques here when calculating these type of limits. So this is the limit as n approaches infinity. Of course, that would become 1 over 1 minus 3 over n plus 1 over n squared. And of course, as we let n grow without bound, these two terms in the denominator are going to approach 0, and this limit is going to be 1 over 1, which equals 1, which very clearly is not equal to 0. And so what that tells me, what I've just shown, is that the limit of the terms in this series do not equal 0. So we can say, therefore, by the divergence test, and I am going to abbreviate DT for divergence test, by the divergence test, the series diverges. There's no way that we can add up an infinite number of terms that each of those terms approaches 1 and get something finite. That is going to approach, in this particular case, that's going to approach infinity. Okay? So by the divergence test, we must know that this series diverges. And just as a little note, this dt, just as a reminder, that is the divergence. I'm going to abbreviate and divergence test. Okay. All right, so let's look at another one that we could actually apply the divergence test to. So for our second example, let's look at this guy. The series is k equals 1 to infinity of 1 minus 7 to the k over 5 to the k. So let's take a look at that guy. I'm going to bring it over here so I have a little more space to work with. And let's take a look at example number 2. So on this particular one, we're going to be looking at the series from k equals 1 to infinity of 1 minus 7 to the k over 5 to the k. Now, little sidebar, side note, we actually have other ways to handle this right now because this is a geometric, well, it's actually two geometric series. So we could split this up. K equals 1 to infinity of 1 over 5 to the k minus 7 to the k over 5 to the k. And we could look at each of these individually. So just side note, we have other techniques. We're just continuing to build to our toolbox here of techniques for dealing with series. So we do actually have another way to deal with this particular series. We could just use rules of summations. We could rewrite this as 7 over 5 to the k, just splitting up that fraction, 1 over 5 to the k and 7 over 5 to the k, where this guy by geometric series r equals 1 over 5, which is less than 1, so this guy converges. So this has a finite sum, but check this out. R here equals 7 over 5, which is greater than 1, so this diverges. So this actually has, and it's a positive ratio there. So this guy diverges, which means this entire series here must go to infinity, but we're subtracting it. So we have basically we have some finite number. We could figure out what it is, but we've got some finite number, and then we're subtracting infinity, which of course is going to be negative infinity, which means that this diverges by geometric series. So we have a way to deal with this. I just wanted to remind you there is a way to deal with this without using the divergence test. Often when we're dealing with series, there'll be multiple ways that we could show convergence or divergence. But on this particular one, we could have gone with our previous knowledge about geometric series. But let's suppose we didn't go that route, and instead we noticed right at the beginning that if I were to take a limit of these terms, so if I take the limit as k approaches infinity of 1 minus 7k over 5k, I could, once again, distribute that denominator and write this as 1 over 5 to the k minus 7 to the k over 5 to the k, which would be the limit as k approaches infinity of 1/5 to the kth power minus 7/5 to the kth power, where as k approaches infinity, anytime we take a ratio to the power that's growing without bound that is less than 1, when that actual ratio is less than 1, this will approach 0. This ratio is greater than 1, so this piece, oh, I just noticed I wrote 5, but that should have been a k. This ratio is greater than 1, so this must be approaching infinity. And again, we get that 0 minus infinity, so we get negative infinity, which is clearly not 0. Therefore, by the divergence test, this series 1 minus 7 to the k over 5 to the k from k equals 1 to infinity diverges. Okay, so this series diverges. And we can show it in either way. We can show it through the geometric series work, or we can use the divergence test here. But if the terms themselves, so just to reiterate on the divergence test, if the terms themselves in a series do not approach 0, then we would know that the series must diverge. Okay, so it's a nice test. It's a nice test to apply at the very beginning of looking at a series, because if those terms themselves do not approach 0, then you're done. You've found the conclusion to what you're looking for. You know that that series must diverge if its terms do not approach 0. Now, on the other hand, there we go. The other hand, we have to keep this in mind. If the terms themselves equal 0, we know nothing, it turns out, about what happens to the series. This, I always say, if the terms themselves equal 0, if we check that and the terms themselves equal 0, well, then that's going to mean to us do more test or do more work. Okay? It's going to mean we don't know anything yet. We still have to do some more work to figure out if we have convergence or divergence. So the converse of the divergence test is not true. It is not true that if the terms go to 0, then we know something about the series. That is not the case. And so just a quick, one last thing as I scroll past here. These are some series rules that we can pull constants out, and we can also split apart series. So we can do that with series. And I just wanted to show this little piece right here to really illustrate that the divergence test, the converse of the divergence test, is not true. If we consider this harmonic series, and this is one we actually looked at the beginning of this section, but this is not one that we can easily come up with the explicit definition for the partial sums, but we can show in a variety of different ways. We can show that this particular series is actually divergent. And you can see here, this is adding up the first 200 partial sums. And you can see here that this partial sum, the sequence of partial sums here, just continues to grow and grow and grow. And in fact, if you were to look right here at the partial sums, this little table down here of the partial sums, where we're taking the partial sums out actually to 10 to the 40th in this table. So 10 to the 40th, notice that that is 92.68. And as we continue to grow, it's not growing at an incredibly fast rate because the terms that we're adding are pretty small, but this partial sums does continue to grow and never hits a finite value. It just grows and grows and grows, which means that this series is not convergent. Okay? So notice that you can see it from the table or from the graph, but in this particular case, the limit as n approaches infinity of s of n is actually infinite, which means that the series 1 over k from k equals 1 to infinity diverges. Okay, so this diverges. And so I use that as a nice illustration, because if we were to actually take the limit of the terms the limit as k approaches infinity of 1 over k, we do get 0. So the terms themselves approach 0, but as we add them up in an infinite fashion, we get infinity. And so notice that this tells me nothing. Okay, so this tells me nothing. I have to do more work. I have to do something else to figure out if the series that I'm adding up actually converges or diverges. So this tells me nothing about, just knowing that the terms themselves go to 0 tells me nothing about what happens if I add them up. Okay, so the series converge or diverge. All right, so I just wanted to end with that note that the converse, right, knowing that the terms themselves do actually go to 0, that doesn't actually tell me much. All it tells me is that I need to do a little more work and figure out the series convergence using some other technique other than the divergence test. And that is it for the divergence test, and that is it actually for our intro into series. And our next step will be to look at what if I do need to do more work to figure out convergence or divergence. And I need more tools in order to do that, and therefore I'm going to go ahead and show you guys a few tests. Actually, we have several tests for convergence that follow this section.